So when we want to visualize hierarchical relationships, there's a particularly good method for doing that called a tree map. So as we visualize graphs, and graphs represent relations between data items, one relation that we'll want to visualize often is hierarchical relationships. Things like parents and child relationships, ancestry and descendant relationships. And so in an undirected graph, if you have a tree, any of these nodes could serve as the root, but often in layouts we can identify a root node, and we can then look at ancestry and descendant relationships based on that root node, based on the edge distance from a node to that root node. In a directed graph, we can set up a more definitive parent-child relationship using a directed edge, and we can have child nodes point towards parent nodes, or the other way around if we set it up that way. We can specify a root node that has no parent in this directed edge representation, and we can create hierarchies where a node could have multiple parents, or we can make them an actual tree, in which case each node has a single parent. And then we can also speak of a tree depth, which is basically, the number of parents a node has at the bottom level of the tree, or the number of descendants, the maximum number of descendants a root node would have along one chain of these edges. And so we often need to visualize these trees. This is an example from genetics of fish, and the nodes in this case are laid out radially, and then the tree structure is shown on the inside. Here's another example from the tree of life, and you can go to this website and zoom in on this image and see a lot more detail than is shown here, but this is a layout that shows a hierarchical relationship as well. One of the methods for displaying hierarchical relationships that I found quite useful is tree maps. Tree maps were introduced by Ben Schneiderman in 1992, and they map hierarchical organizations of quantities into areas. So it's a very visual method for displaying hierarchies based on subset operations. And so we have an example of this in a utility called WinDirStat, which displays a Windows file system, and it represents the entire file system by this rectangle. And then that root directory is subdivided into smaller rectangles representing subdirectories, and each smaller rectangle is subdivided into smaller rectangles, which are subdirectories of that subdirectory, all the way down to individual rectangles, where each of these individual rectangles represents a single file. And so it gives you this nice broad overview of your entire file system, but it also shows you how the file system is divvied up into individual directories and subdirectories and files. And so it's a good indication of quantitative views. In this case of disk space, it's telling me how my files and subdirectories are taking up different amounts of disk space. And so it's mapping disk space to area, and I can get a pretty good quantitative measure of that disk space based on the area relationship of each of these subrectangles. So how do we compute a tree map? Well, if you're given some hierarchy, some tree, and then you've got, and for a tree map it has to be a tree, it can't just be a regular hierarchy. Each node has to have a single parent. You have some value usually at the bottom level. For that previous example, this would be the files, the disk space taken up by each individual file. And so we first need to do a bottom-up procedure that takes our tree nodes, and for the parent nodes of our tree, adds up the child nodes in order to assign them a value. So now each of the parent nodes is equal to the sum of its child nodes. This parent is equal to 4, it's 1 plus 2 plus 1. This parent is equal to 11 because it's 4 plus 4 plus 3. And finally 16, which is the sum of all of these, adds up to 16. And then we're going to use that parent-child relationship and the values that it represents in order to subdivide some rectangular region in order to display how these small quantities at the bottom are organized as portions of this full 16 value at the top, at the root node. And so the first thing we do is we need to subdivide our rectangle into portions representing the first set of descendants, 11 and 5. And so we subdivide the rectangle into a portion that's 11/16 and 5/16. And so we subdivide it horizontally with a single vertical division at 11/16 of the way from this edge to this edge into a portion that's 11/16 and 5/16. Now we have two portions, and these portions are actually taller than they are wide, so we're going to subdivide them vertically instead of horizontally for the next step. So now we've got this portion here on the left representing 11. We need to subdivide that into portions representing 4, 4, and 3. So we subdivide them into a portion that's 4/11ths along the way, another 4/11ths along the way, and then finally another 3/11ths along the way, representing each of these three nodes. And now these are wider than they are tall, so we're going to subdivide them horizontally instead of vertically at the next step. And so we do this again, and we subdivide this this top node into 1/4, 2/4, and 1/4 portions horizontally. And we do this with all the rest of the nodes, and we get this tree map of all of the nodes we see here. And so here I've got 1, 2, 1, 1/2, or sorry, 1/4, 1/2, 1/4 of this rectangle representing 4 units. I've got 1, 1, and 2 of this rectangle representing 4 units, and then 2 and 1 of this rectangle representing 3 units. All together, those represent 11 units. And on this side, these 5 units that were 5/16 of the entire triangle are being represented by 3 and 2, and I've got a slightly thicker line here differentiating between them. And then this 3 unit is by individual units here, and this 2 unit is by individual units here. And so we're using area and a hierarchy of area into finer and finer rectangles in order to divvy up this large rectangle into its component pieces. You'll notice that, for example, this rectangle here is 11/48 wide because it's 1/3 of 11/16. It's 1/3 of the 11/16 on this side of this thick black line. So 1/3 times 11/16 is 11/48. This bottom, the height of this is equal to 3/11. It was 3/11 of this whole unit. And so we have 3/11 times 11/48 is equal to 1/16, which is exactly the portion 1/16, where is it? Right here, 1/16 of the entire area that we wanted to represent. And so that gives you a good visual connection between the area of this tree map layout as a portion of the whole and the organization of this node representing 1 unit of this parent of this root node representing 16 units. You can also see some of the difficulty in doing ordinal connections between area. This is 2 units of area, and this is 2 units of area. If I didn't have these numbers here, it may not be as easy to see that this rectangle is the same area as this more square region is. So area is not that good at representing ordinal amounts, but it is a pretty good tool for representing quantities in general.
So the tree map is a good method for visualizing hierarchies because it relates the region of that hierarchy to a region on the screen, associating it with area. But as we've seen, area can be a decent but not great method for ordinal relationships.